Today we're going to talk about imaginary numbers. So in the past, when we looked at an equation like x squared equals -1, and we went to solve this, we would take the square root of both sides to get rid of this square. So that canceled out and gave us x squared equals plus or minus the square root of -1. Now this cannot happen. We said that's not a real number. You can't take the square root of a negative. And so we're going to talk about imaginary numbers to help us with this problem. So the imaginary number I is the number such that I squared is equal to -1. Because no real number exists such that its square is equal to a negative number. The number I is not a part of the real number system. So it tells us that I squared is -1. So if we consider that to figure out what I is, we would take the square root of both sides here. And so I is equal to the square root of -1. Those are the two that you really need to know. I is equal to the square root of -1, and I squared is -1. Now, before we get to talking to the rest of those, I do want you to see that the calculator will do this as well if you change it from the real number system to the complex number system. So we go to mode, and then we go down over here, and instead of marking it with real, you're going to go to the A plus BI. That's the complex number system. Now, when you take the square root of -1, it will tell you it is I. All right, so we defined I to be the square root of -1, and I squared to be -1. If we think about I cubed, that would be these two multiplied together. So that would be the square root of -1. Remember, when you're multiplying bases with the same bases with exponents, you add the exponent. So 1 plus 2 would give us a 3. To get I to the fourth, we would do I to the third times this I right here. So if we multiply these two together, a positive times a negative is a negative. And then the square root of -1 and the square root of -1 would cancel out the square roots. So that would be -1, which gives us a +1. When we go to I to the fifth, then we would multiply these two together, and 1 times anything is itself, so that would be the square root of -1. To get I to the sixth, we would do these two together, and when we multiply these two together, the square roots cancel, and we get -1. For I to the seventh, we would multiply these two together, and a -1 times the square root of -1 gives us negative square root of -1. To get I to the eighth, we would multiply these two together, and that's the same thing that we did here, so we're going to have that 1 again. And hopefully you see a pattern at this point. Every fourth one is exactly the same. So when we get to I to the ninth, it's going to be the square root of -1. I to the 10th is -1. I to the 11th is the square root of -1, and I to the 12th is 1. So this pattern repeats every fourth one. So you can use that to calculate I to a higher power by thinking about the way it repeats every fourth one. Many times on ACTs and SATs and college entrance exams, we'll see stuff like this where it says I to the 93rd power. What you need to do is think about I to the fourth power, because you can remove all of those. Use those exponent properties to reduce that number to something that you know off the chart. So we can raise I to the fourth power to the 23rd power, and that gets us to 92. So we need one more I. Remember, when you have a power to a power, you multiply. So 4 times 23 gives us that 92. And then one more I would give me the 93 that it's asking for there. So I to the fourth is 1. So basically all of this is 1 times I, which we said is the square root of -1. So by knowing those four, you can go ahead and reduce that down to what it is easier. So again, we think about that as I to the fourth because that's just 1. I can raise that to the 51st power because this is 206, and 4 times 51 will give us 204. And then we just need 2 more, so an I squared. And we said I squared is -1. So we can simplify that to be -1. For I to the 400, I go I to the 4th raised to the 100 power, because 4 times 100 is 400, so it is just 1. And then for a negative exponent, remember that just means that it is going to flip over. That negative does that 1 over. And so we get 1 over I squared, and we said I squared is -1. So this would be equal to -1. So that helps you reduce them down as they are bigger exponents. Now we're going to practice simplifying these so that you can see how the I works. Before we get to these examples here, I'm going to quickly show you in the calculator how that works and off to the side. So in the past, if we were taking the square root of -36, we would say that was not a real number, which is exactly true. But there is an imaginary number. We can simplify this to be the square root of -1 times the square root of 36. So we have defined this to be I, and we have defined this to be 6, because the square root of 36 is 6. And so this is equal to 6I. That's how we're going to use that square root of -1 when we're solving, by defining that I. Your calculator, again, will also do that. So if we hit second square root, now that we've changed the mode, when we hit -36, it tells you it's 6I. So that's how we use that to simplify and solve problems that have no real solutions. So on a problem like this, we would take the square root of 64, which is 8, and then we would want to take the square root of -63. Now in this one, there's a combination of things that are happening there, so I'm going to go ahead and reduce that off to the side. So first we would want to take the square root of -1 out times the square root of 63. And back in geometry, you should have learned how to simplify this square root of 63. You either did that with the little tree or you did your biggest perfect squares. So I'm going to go ahead and do the biggest perfect squares. And so I separate the biggest perfect square that goes into 63 is 9. 9 is the same thing as, 9 times 7 is the same thing as 63. So -1 times 9 times 7 would give me this -63 we started with. I'll go ahead and put that. Those are all equal to each other. And so now we can simplify it. This is I, this is 3, and this does not simplify any further, so it stays inside the house there. And so we would get 3I root 7. Now to write this correctly, the I would be at the end. I go ahead and write it here because a lot of people make this line too long and it stays underneath the square root, and it should not. So you could write this 3 square root of 7 with the I at the end so that it's in the correct format, but you want to make sure it is outside of that square root. So it is okay if you write it this way. That's how we simplify that. I did not put these two together because they are not like terms. So it kind of gets treated like a variable where you're applying those same rules. If they're not like terms, you cannot put them together. All right, so here is another one. The square root of -13, well, there's no perfect square that goes into that. So the only thing I can simplify that to be would be I root 13 plus 10. They are not like terms, so I cannot add them. But we usually write imaginary numbers in the format of a plus bi. So your real number plus your imaginary number. So we get 10 plus I root 13. All right, this last example is pretty important because this is where we're going to get to with the imaginary numbers. When we're solving the quadratic formula, we're going to want to have some imaginary solutions on the ones that have a negative under the square root. So we'll go ahead and simplify this. Again, we would take the square root of -44 and we would separate that into the square root of -1 times the square root of 44. And then I can go ahead and find the biggest perfect square that goes into 44 is 4. So I do the square root of 4 times the square root of 11. negative 1. Negative 1 times 4 times 11 gives us this negative 44. So I've not changed the value of it. I've only separated it so that I can simplify easier. So this is I, the square root of 4 is 2, and there's no square root, or the square root of 11 is irrational, so we're going to leave it as the square root of 11. So here we get 1 minus 2i root 11 over 2. And this is a perfectly good answer right here. So this would be a possibility on your simplification of the quadratic formula. You could also change it to 1/2 because 1 divided by 2 minus the 2 divided by 2 is just 1, so I root 11. Either one of those would be a correct answer. All right, so the set of complex numbers is the set of all numbers written in the form a plus bi, where a and b are real numbers. The term a is called the real part of a complex number, and the term bi is the imaginary part of the complex number. So when you have an I in there, it is part of the complex number system. When it's just a number, that would be the real number system. Even if it's negative, it's still part of the real number system since it does not have the I. And then when we have an I, it is a complex number. So there is that. All right, we're going to talk about simplifying these when we have them in the format like this. You can add, subtract, multiply, and divide complex numbers. Again, you treat them kind of like a variable. So when I am simplifying this, I have the parentheses here minus this parenthesis. Remember this minus you have to distribute all the way through. That makes it the easiest possible. So we get 3 plus 2i minus 1 plus 6i. When you distribute that, negative times a negative gives you a positive. And so to finish this problem, we would combine our like terms. 3 and negative 1 are the real numbers. So I would combine those to be 2, and 2i plus 6i gives us 8i. And so here is our answer. Same thing here. Anytime that you're adding and subtracting, you are combining your like terms. So we've got a 3, a negative 6, and a negative 1. That gives us negative 4. So 3 minus 6 is negative 3, minus another one is negative 4. Then we put the I terms together. So these two are the ones that are going to go together. We have a 4i and an I, which is 5i. Here is another example. We combine our 4 and our negative 10 to give us negative 6. And then 7i and negative 2i give us a 5i. So we have negative 6 plus 5i. And for our last example here on the adding and subtracting, we combine our negative 4 and our 7 to get 3. And negative 2i and negative 6i give us a negative 8i. So with adding and subtracting, you are just combining like terms. With multiplication, you can multiply an I times a real number. So when we have something like this, to get rid of the parentheses, we would want to distribute that 5i all the way through. So 5i times 3 gives us 15i, and 5i times negative 2i gives us a negative 10i squared. I multiplied the 5 and the negative 2 to get negative 10, and the I times the I gives us I squared. We would not want to stop here because we know that I squared is negative 1. And so when we simplify this, negative 10 times negative 1 gives us a positive 10 plus 15i. Remember, the real number goes in the front and the imaginary one goes afterwards. All right, same thing goes with a 2 parentheses like this. In the past, when you did this, you either did this through box or you did FOIL or distribution. You can do the same thing. Even if you use a box, you can go ahead and do the box with that one. All you have to do is 5 and 3i, and 2 and negative 3i. The 2 and the 5 give us 10. 2 and 3i give us 6i. Negative 3i and 5 give us a negative 15i. And negative 3i and 3i give us a negative 9i squared. When we combine our like terms, we've got a 10 here. These two give us a negative 9i. And this one is a negative 9i squared. Now again, you do not want to leave an I squared because you know that's negative 1. So that would make this a plus 9. 10 plus 9 is 19 minus 9i. All right, we'll do another one over here. For C, I'll do this one by multiplying it with the distribution. 2 times 2 gives us 4. 2 times negative I gives us a negative 2i. I and 2 give us 2i. And positive I and a negative I give us a negative I squared. Now to simplify this, negative 2i and positive 2i cancel each other out. And so we have 4, and I squared is negative 1, so that turns this into plus 1. So this would be just be 5. The imaginary number part went away. The last thing we're going to talk about is complex conjugates. They're pairs in this format right here, A plus BI and A minus BI. Those are considered conjugates of each other. That's important because we're going to use that sometimes to fix our denominator so that we don't have an imaginary number in the denominator. So complex conjugates is when you have a positive BI and a negative BI there. So one is a positive, one is a negative. And so we're going to see how that works back here on our rewriting these with the conjugate. So 7 plus I would be 7 minus I. That would be the conjugate. For negative 5 minus 3i, that would be negative 5 plus 3i would be its conjugate. And for C here, it would be 12 minus 11i. And then for D, you would have a positive 4i. And so the reason why we do that is because it helps us to change when we have that as a divisor. So we are going to multiply these two together so you can see what happens when we multiply conjugates together. So 7 plus I times 7 minus I. The 7 times the 7 is 49. 7 times negative I gives us a negative 7i. I times 7 gives us a positive 7i. And I and negative I gives us a negative I squared. This negative 7i and positive 7i cancel. And we learned that I squared is negative 1, so this turns into a plus 1, and we get 50. So we have lost the imaginary part to that. That is going to be true every time you multiply times the conjugate. So we'll try another one here, negative 5 minus 3i and negative 5 plus 3i. That's basically the difference of squares there, so it's going to cancel again. Negative 5 times negative 5 gives us a positive 25. Negative 5 times 3i gives us a negative 15i. Negative 3i and negative 5 gives us a positive 15i. Negative 3i and positive 3i give us a negative 9i squared. The negative 15i and positive 15i cancel out since those are both the same term with a different sign. I squared is a negative, so this turns it into positive 9. So 25 plus positive 9 gives us 34. So the I is going away. That is even going to be true when there's no real number here. If we multiplied negative 4i and positive 4i, that gives us 16i squared. And the I squared is negative 1, so that is negative 16. You'll use that later on to remove imaginary numbers from the denominator.